Welcome to Science, everybody. So, dice as a model for radioactive decay. In real life, here's what goes on. Looking at this reference table right here, which, by the way, is your final reference table, page one of their science reference tables. Carbon 14. It's an unstable form of carbon. It's a carbon that has too much going on in its nucleus to simplify nuclear chemistry down to a tiny little bit. It's not happy like it is, so it's going to shed some of what it is to be happier. To be more stable is the term we should really use. It breaks down to a more stable isotope. So does potassium 40, so does uranium 238, so does rubidium 87. So the thing about this is that we can use the rates at which they decay to act as like a timer, really, on geologic events. Now, the trick to it is, this is complicated stuff. The trick to it is that any one individual carbon 14 atom breaking down into nitrogen 14 is a random event. If I could somehow put that on the table in front of you and say, watch this until it breaks down, maybe you'll see it happen, maybe you won't. So, what can we use that is like random, that we could set up rules so that it decays randomly through time and then study the math? Well, we used dice. So if you were here the day we did this experiment twice, one with a 6-sided die and once with a 20-sided die. And here's the end results. Even though any individual given event is random, by the time that we threw together, by the time that we threw together all of the data, we end up getting these very predictable curves that year after year after year work out pretty well. In fact, this year is the least accurate that they've been in all the years I've done this experiment. Which, sometimes it happens. Maybe we counted wrong. Maybe some people that were rolling, got distracted. Who knows? But either way, it still is pretty predictable, even if it's off by a little bit. And here's the premise. How long does it take for half of them to go away? So in other words, at the beginning, we had 100% of the dice. We had all the dice we used. We set up the rules to say, okay, everybody roll every 15 seconds. And when a 1 comes up, we're going to say it decayed. That random event of a 1 coming up means it decayed, it went back into the box, and it's gone. All the other numbers stayed on the table until the next 15-second interval when they'd roll again. So how long did it take for us to lose half of them? Like 50% of them. It took that long, time-wise, however long that is. That's what we're going to call its half-life, the amount of time it took for half of them to go away. Now, it may be logical to think, well, if it took that long for half of them to go away, it'll take that long again for the other half to go away. But that's not how it works. Now, because of odds and because of how this all, random events work, it should take the same amount of time for half of them to go away again, which means we went down to 50% in the first trial. The second trial, if 50% are left and we cut that in half, we're going to go down to 25%. And we look and we see that it takes about the same amount of time. And then how long for half of those to go away? How long until it's at 12.5%? And if, again, if this all works, it should take about the same amount of time. Our numbers came off a little bit. We can still do the lab, though. Not worry about it. That's the premise. That's complicated. And it's a big ask from me to say to you, hey, how does rolling a bunch of dice mimic the processes that are happening on a atomic level with radioactive isotopes? That's confusing. You know what I'm saying? But hopefully we simplify it a bit by just like modeling it and doing it and running the numbers. We'll see if we can make some sense out of this. It's gone pretty well for most people. You will do great too. So the whole premise here is to understand radiometric dating, a technique that allows us to calculate the age of an object based on the predictable. I would like you to circle predictable. We're going to take a quick note on that. Disintegration of radioactive isotopes. The note I'd like to take, I'm using the wrong pen. There we go. The note I'd like to take is it being predictable. What does that mean? It means that the rate never changes. Okay, so like what might change the rate? Well, nothing does. But what people maybe, I don't know, what you would assume would change the rate, even if the temperature changes or the pressure changes. Temperature changes don't do anything. don't change the rate. Otherwise, we wouldn't be talking about this. Otherwise, this would be a useless tool in geology. But since temperature changes and pressure changes to the rock don't affect the rates that these isotopes decay at, we can use it as a timer. And it's just like, find out where you are on this timer. If you know how many half-lives that is, we can calculate what the half-life is in a lab fairly simply, and then just see how much is left. Run the numbers, and you got yourself the age of whatever it is you're looking at. It's a very complicated tool, but at the end of the day, it is that simple. It's just like, if you know this rate, just find your spot on the line, and boom, time-wise, you got it. And it's like unraveled all of geologic history, so it's great. So radioactive isotopes, like carbon-14, predictably decay down to a more stable isotope. So specifically for carbon-14, it changes to nitrogen-14. I'm going to write that because it's kind of tricky. 1, 4, N. Or potassium-40 decays into those two, or uranium-238 decays into lead-206. You don't have to memorize any of these. This is a reference table after all, right? But it predictably happens. And although any individual one is a random process, just like rolling a die, the amount of time it happens over a given time period, the number of like individual decayed atoms that takes place is predictable. What we look for is, what is the amount of time it takes for half of a sample to decay? That's known as the half-life. And again, this curve is just a matter of where to go. This curve is just a matter of basic probability. This is done with dice, but the radioactive isotopes work exactly the same, which is kind of neat. So it's really just a study in statistics more than it is in geology. All right, so you got this reference table. You can find that ESRT page 1. So keep that in mind. It's on the front cover. We've got 3 different isotopes. The top one, this pops up in a couple questions, as does this. This will be in a question or two. So hold on to that in your noggin for later, or just scroll back up here. The top one, carbon-14, this 5.7 times 10 to the 3 means it grabs that decimal and go over 3 spots, which would make it 5,700 years. This is going to be good for things that are reasonably young. I know 5,000 years feels like a long time compared to like your lifespan, but in geology, going a couple of half-lives with this, so staying maybe in the neighborhood of between 0 and say 20, 30,000 years, that's young geologically. These guys down here have a half-life in the billions, so these are good for things that are very old rocks. So if you got to test things that are more young, like since the glaciation, since the Pleistocene, carbon's a great tool. Excuse me. If you've got to test things that are like very old, like the age of the rocks up in the St. Lawrence River Valley, then you're going to need a tool that's more appropriate. Isotopes with a longer half-life. Because think about this. If we had something, those rocks up in the St. Lawrence, different areas, let's say they're 1.3 billion years old. If I go back to my graph, if this like gets so flat that you can't tell, that you can't tell the difference anymore, by the time it gets down here, it's just like flat. What if you take half of that? You can't tell. And half of that, you can't tell anymore. You kind of run out of usability here. So carbon-14, by the time you got to something being millions and billions of years old, would be negligibly small. We're kind of happy in the zone of maybe like 0 to 4-ish, 5-ish half-lives before we really get down to a useless percentage. So test things that are young with carbon-14, test things that are old with these other 3. That idea will come up in questions. So what we did, I'll start writing less so that we can get through this thing. We rolled dice. And I used to do it with standing and sitting. This year was just ones go in the box, everybody else keeps rolling, right? We did that to mathematically calculate this. How long was it until basically half the dice ate or went into the box. So we measured that time, and then if you run that amount of time again, what percentage should still be left after 2 half-lives? Well, 0 half-lives, you got 100%. 1 half-life, cut it in half, you got 50%. The next half-life, cut it in half again, meaning you're down to 25. If you guess 0 there, you're missing the idea that you only get rid of half of whatever you have. So after 3 half-lives, you'd be at 12.5%, and so on. How are the D6 and the D20 different? Well, if you were here, you realize that the D20 one took a lot longer to do. And it's because there's 20 sides on it. There's only 1 so it's a 1 in 20 chance of getting a 1 on that versus a 1 in 6 chance of getting a 1 on that. So the D6 experiment basically went faster. That's why the idea is that things like carbon are good for young things. They'll run out of carbon in a faster amount of time, whereas the D20, the experiment was slower to show us the idea of other isotopes that degrade slower are good for things that happen over a longer period of time. Okay, now you need your data, which I have on paper. It's probably easier to do on paper. See me if you need it. Let me find it digitally. One sec. Okay, so your results are right here. Again, I'm going to recommend coming and see me and getting this on paper. It just makes your graphing easier. Here's the amount of time we took. Each time we rolled, we let 15 seconds pass. That was about enough time to roll, look at the results, put the ones in the box, get back, have me count them, and all of that. So every 15 seconds was another trial, because that's how long it takes to roll a die once. And then this is how much was remaining, according to our experiment, after that much time. This column for the 6-sided die, this column for the 20. And then these, I just did it over 3 columns. It just keeps on going. This is really down there. Doesn't want to let me move it, but you see what I'm saying? The 465 is right after the 450 down here. So it's really one set of data spread over 3 columns. So it can fit on paper. So what's our job? Too many windows. So according to our data, how long did this take? Well, we had 100% after 0 seconds of experiment. There was all of it, right? How long for the D6 did it take to get down to 50%? D6 got to 50% or right about there, say after 45 seconds. So then another half-life would get us down to 25%. How long did that take? In this case, it worked out pretty well, right about there, at 90 seconds. That's wonderful, because that shows us that after that much of an interval, we lose half again. Now, this one is where it gets a little screwy, I think. Let's see, 12.5% was at about one, I don't know, we'll just go with that 165. Which is going to be more, I think, people's attention spans maybe wore out a little bit. Or maybe there was just an anomaly that time. It is a random process, right? Or maybe I counted wrong. I'm failable. But it's all good. We're gonna play with this lab either way, rather than starting all over. And the next one looks like it's at about 225. So what are the half-lives? It went from 0 to 45. That's 45 seconds. Then it went from 45 to 90. That's 45 seconds. Then it went from 165 to 90. That is 75 seconds. I hope I don't make arithmetic mistakes here. Then I went from 225 to 165, which took 60 seconds. So 45, 45, 75, 60. If I average those, 225 divided by 4, about 56 seconds. So we're saying in this experiment where dice takes about 15 seconds to roll, every 56 seconds, we should lose half of them. If I started with 100 dice, it should still work. If I started with 1,000 dice, it should still work. About every 56 seconds, we'll lose half the die. How about the 20? Well, that took longer because there's less of a chance. So it's still 100 is at 0. We didn't get down to 50 until right about there. We'll say we passed it when we get to the 210 second reading. So 0, 210. These are in seconds. 210, that should say seconds too. When did we get to 25%? Looks like right there at 465. When did we get to 12.5? there at 885. And when do we get to 6 1/4? Right about there at 1140. So 210. 255. Not terrible. 420. That's where something got screwed up. Again, my guess is attention span. 1140 minus 5 is 255. So that, hey, look, there's a little stability. All right, so 210, 255, 420, 255. Comes out to about every 285 seconds, we should lose half of the D20. All right. So random occurrences, you lose half at a very predictable rate, even if we had a bit of an anomaly this year. We'll try again next year. Come on back. So if we had to make a reference table out of this might feel silly, but I do it so that we really see like, hey, okay, this reference table here, what does it mean? It means you take this thing, which I'm in a ridiculous sense calling D6ium, and we're disintegrating. We're going from one thing to another. I should be using the mouse to point. From this to this. What do we do in the lab with D6ium? We said that it went from basically rolling die to box. That's when we got rid of the die. It went to the box when we rolled a 1. Our half-lives that we came up with are in seconds. That it should take 56 seconds for 6-sided die and 285 seconds for a 20-sided die. Yeah? Again, just to bring it back to this, just like this isotope goes to this isotope every that much time, every 5,700 years, or every 1.3 billion years, or for that, every 4.5 billion years, and so on. Okay, almost with me. Almost done, I should say. Thanks for sticking with me this long. Graphing. You'll need this data sheets. What we're going to do is do one graph for the 6-sided die, one graph for the 20-sided die. I set it up so that along the bottom is time in minutes. If you want to be a little grumpy with me over this, I put this in seconds, the other one's in minutes. So you got to be clever enough to know that like 60 seconds is a minute, but I think you're there, right? The one thing I did do is say every box is 15 seconds. So basically every box on the x-axis was one of our die rolls. And all we're going to do is plot as we go. Now, if this looks like a bajillion numbers and you're going to say, I don't want to do it, don't worry. By the time people complained because they saw all those numbers, by the time they did it, it's really pretty easy. And also, think about this. Once you get to here, we know what's happening. You don't have to go and plot every single one of those dots. It's stuck at that bottom. So I'd say maybe plot like roughly this area. And then once it's flat, you can kind of just, you can chuck dots and it'll go very quick. Okay. It should look like that, roughly. How do we do it? At 0 seconds, we had 100%. So go to the lab. Get your drawing. At 0 seconds, we had 100%. Dot. One reading over. At 15 seconds, we had 87.5. Dot. At 30 seconds, we had 70. Dot, and so on. Do that. It'll get down here. Then you can just make it flat. Then you got another one here for 20-sided die. You can do that. You'll be in good shape. Okay? Questions are going to be where you got to think a little bit. This is a good first question because we could fill this whole thing out. I always use this as the first question on this lab, even when I did this lab totally different. Because this is how these questions are really principally all going to work. This column, here's how many half-lives have taken place. Here's how much percentage-wise should be remaining. I used to draw this in the margins of my test back in the days when I was doing earth science, back in the I don't know, 92 or so. 100 cut in half, you're at 50. Cut in half, you're at 25. Cut in half, you're at 12.5. Cut in half, you're at 6.25. Cut in half, you're at 3.125. Carbon 14, yes, for other isotopes, it's a different amount of time, but for carbon 14, according to our reference tables, it's 5,700 years. So add 5,700, add 5,700, add 5,700. You'll get what? 20. I'm doing my math right here. We've gone this long in the video. I might as well be right? 17. Hey, what do you know? And then 28.5. Like this part of it is always the same. If we get rid of carbon 14, especially, this many half-lives means this percentage is remaining, even if it's dice we're talking about. All that we're adding then is how many years did that take according to the reference table, with carbon 14 having that one. When you get over to this question, they're asking you about K40. So what you got to do is be clever enough to go back to the reference table and say, oh yeah, this is the same question. They're just having me do it with potassium 40, which has a half-life of that long, and figure it out. And you can do it. Thanks for sticking with me. I know this was long. How long do we go? Oh, 20 minutes. All right, good luck, everybody. Finish that up, get it in. And congratulations, you're done with labs. So long.